I am Elias. I am now a staff product manager at DBT. I was the co-founder and head of product at SDF. If you are so inspired by this conversation that you want to message me, you can. Add that email right there. It's a DBT Labs email. I have to get used to that. And so let's fast forward backwards to before DBT came along. There was a problem in the market. A developer framework was needed for data practitioners. It was very clear. We started interfacing with OLAP engines in the cloud. We started piecing together SQL queries via stored procs and a bunch of other mechanisms. And DBT came along and provided us with a developer framework. But I believe DBT got 80% of the way there with 20% of the work. And so there's an 80-20 principle, common sort of idea, that it takes 20% of the work to get 80% of the way to a solution towards something, or to build something. And then it takes 80% of the work to get the last 20%. And so I believe this is the first 80% of the right developer framework for data practitioners. DBT introduced the model, a construct we've all become very familiar with, right? A model represents a state in a database in combination with a version piece of code that produces that state. DBT then intelligently pieces together these models into a DAG and runs them in the right order for you. It adds a testing framework on top of that so that we can assert the quality of the data produced by our code and models. It adds a documentation framework and even a library ecosystem around DBT packages. So all these things, you look across other developer frameworks, TypeScript, Java, Rust, you have testing, you have documentation, you have libraries. DBT got us 80% of the way there. But, what's going on? This worked so well that all of you and many, many other millions of people around the world adopted it like crazy and started using it more and more. And as such, I believe the DBT framework hit what I consider like an innovation plateau. And this is not a diss against the amazing, brilliant DBT team that I've come to work with quite closely in the last 4 months. This is rather just that they had to support this incredible growing community and could not invest the other 80% of the work to get that last 20% of developer framework over the line. Why would you? You do a little cost-benefit analysis. It's like, why would we spend 80% more of the work if our users are growing rapidly, right? So it made sense. But it also produced an opportunity in the market for people like me and my co-founders to build the other 20% and improve the experience. So what is that core problem statement? Is really that I believe the DBT core framework is behind today's standards for developer experience. If you look across TypeScript, across Rust, across Java, other modern development frameworks, it's not there. And why is that? What is the other 20% that it's missing? Well, to start, it's local emulation of cloud execution. In any developer framework where you can run things locally that will then be deployed to the cloud, you as a developer can move faster, much, much faster. And that is a good thing for everyone. You even look at like Kubernetes. Kubernetes is a huge backend orchestration and networking layer, right, that hosts a huge amount of services in the cloud. You can even run that locally with Minikube, and it gives you nice emojis in the CLI output. It's a great developer experience. But that is missing in the world of data development. A language server protocol, an LSP, right? This is commonplace in languages like TypeScript, Java, Rust, the ones that I brought up. Even Python has several attempts at an LSP. This was a protocol introduced in the 90s by Microsoft, and it's become the standard for how code editors and IDEs power things like autocomplete, IntelliSense, spell check, right? Imagine using Google Docs without spell check. All of this puts the developer on hyperdrive. Super freaking fast performance. Speaking of putting things on hyperdrive, this is trademarked, by the way, so if you take a photo of this, I will find you. No, I won't. Even if we can run things locally, it doesn't matter if the engine dealing with my code is slow, right? I'm still slowed down and bottlenecked as a developer. AI readiness, right? AI is bottlenecked by the same things that we are as developers. When it produces code, it needs to validate that code and assert it correctly. And if you are unable to run the validation system, the code interpreting system locally, and if you don't have an engine with fast performance, if you don't have extra metadata from a language server, it's very hard for AI to do a good job, right? This is why we see AI doing incredibly well on compiled languages or attempts at compiled languages like TypeScript, right, which have incredible amounts of code in the wild, LSPs, right, a compiler to validate the code in real time. And lastly, I'll point out another one, polyfills. You'll notice a trend here. A lot of these are like JavaScript or TypeScript references. I started my career in full stack, so I've got a lot of inspo from that. But polyfills, for example, in JavaScript, I can write one piece of code, and polyfills will handle, at compile time, ensuring that same code runs the same way on each browser. So Internet Explorer, Firefox, Safari will all run my JavaScript the same way. In the world of data, this would probably be compute retargeting, right? Where I can take one SQL statement and I can give it to this developer framework, this engine, and it will run it and produce the same results no matter the engine executing it, whether that be BigQuery, Snowflake, Redshift, right? So what's the common thread between these? The common thread, outside of super freaking fast performance, is that you need a deeper understanding of the language you're working with, right? Today, dbt resolves Jinja and defers SQL understanding to the cloud warehouse, right? So to power local emulation of that cloud warehouse, to power an LSP, compute retargeting, you need a system that runs locally with a developer framework that understands the SQL it's dealing with. So, not so hard, right? Let's build something that understands SQL so well that it can execute it in every proprietary dialect that sometimes is not documented. We're going to play a game to figure out why this is so hard. Okay, so on the top we have databases. On the left we have column identifiers, right? So imagine you're doing like a DDL, or and you select some columns, or you do a create table, right? And we're all going to determine if each of these databases says that this is a valid identifier. Okay, on the top left we have foo. It's just strings. Where do we stand? Yes, I'm seeing a thumbs up. Across the board, we're good. Good job, databases. You've come together and decided foo is a valid identifier. Foo1, we add a number into the mix. We're also good. Good to go. Foo bar, capitals. Uh-oh, I'm going to trick them up? No, not yet. Foo space bar. Ah. If they did support this, that would be criminal, to be honest. But they don't. Thank God. But uh-oh, double quotes foo bar. Now we get some discrepancies. BigQuery calls it a day. It says, nope, I don't like the double quotes. Backtick foo bar, however, BigQuery says, I'm in. Snowflake also says, you know what, I'll join the party here too. Redshift Trino, they're out, right? Foo new line bar in the backticks. Well, Snowflake calls it a day. It says, I just can't deal with a new line. But BigQuery is still holding strong, right? How about keywords, right? So these are actual keywords that act as like SQL keywords. Order. If everybody knows this, I'd be very impressed. Turns out Redshift thought that parsing the order keyword as a column name would be a differentiator for them as a database. I don't think that worked out. But then we have minus, which they all agreed on except Snowflake said no. Too hard to parse that. So even identifiers, a fundamental unit in the sort of parser or compiler of these systems, it's totally crazy and does not follow any logic or rules. And so that's the real challenge behind the other 20%, is to faithfully parse, compile, and execute every dialect of SQL in a single engine. Do all of that on the right-hand side. Parsing, producing a syntax tree, binding the types into a logical plan, optimizing and planning into a physical plan that can be run locally on one system, right? That ideally also maintains really good performance because of the sort of requirements we laid out earlier. But maybe you're out there, you're thinking, you guys are a smart crowd here. Maybe you're thinking like, I don't know, I could do this. And honestly, that's cool. That's great. Your name might then be Wolfram Schulte. There he is. Wolfram, yes. And this is my co-founder and CTO of SDF. And so if you were Wolfram, you would probably call this thing you'd create SDF. and you would say this is a blazingly fast multi-dialect SQL compiler, transformation framework, and analytical database engine. So let's go through each of those. SQL compiler, that means we can take SQL of any dialect and resolve it to one unified logical plan for analysis. Transformation framework, this is what DBT does today. So this is producing a DAG, running the models in order, testing those models, documenting them, all the wonderful developer framework features. And an analytical database engine, just like the guy who I am following here. Building a system that can actually run those queries locally, take that logical plan, and produce a physical plan for execution, right? And maybe you would continue on and you would create an architecture diagram. Cool. And on the left, we have SQL dialects coming in. Snowflake, BigQuery, Databricks, Trino, Redshift listed there. Those are the ones we supported. And you would have a system that would then take those and like I mentioned, produce a unified logical plan. You would then ingest extra metadata from the user, like descriptions, tags, or metadata remotely from the warehouse, like column types for DDLs that are not present in the system, right? You would run some awesome static analysis, and then you would do a bunch of cool stuff downstream of that. You would produce valuable metadata like column level lineage, like rich data flow understanding. You would power a language server, like an LSP. You would optimize task scheduling and produce a DBT manifest file. You would lint and format SQL very fast. You could even execute that SQL and translate it, which in a system like this means taking that logical plan and rendering SQL back out into a chosen dialect. Cool. So, you've created the architecture diagram. How would you do it? How would you actually build this system? Well, in all your brilliance, you would figure out that as much as this is a technical problem, it's also an operational one. Because the sheer amount of code required to emulate each of these database systems in one engine, how do you maintain and construct that breadth, right? Especially when you're not Microsoft and you don't have millions of dollars, hundreds of millions to spend on top-tier developers, right? When you're a startup. Well, you'd likely conclude that you need automation and you need some way to easily maintain the rule sets for each of these parsers and compilers. Maybe some of you know where I'm going with this. Easily maintain rule sets. You probably want a higher level language. You probably want a DSL, a declarative one that allows you to easily tweak the parser. Yes, I am getting at a grammar. Cool. And so this was sort of the fundamental innovation, the parsing layer, that enabled us to accurately emulate and maintain parsing of each of these specific dialects. What is a grammar? A grammar is a high-level DSL, declarative, for representing a parser and a few other things along with that. And I'll go a little deeper. But in this case, we used Antler. Stands for another tool for language recognition. On the left-hand side, you have a SQL statement that comes in. And you can see the Antler grammars down below. These are, so this high-level representation, the G4 files, they're called. We would generate a parser for each dialect. So in this case, we'd generate one for Snowflake. Produce a Snowflake-specific concrete syntax tree. Many of you have probably heard of an abstract syntax tree. This is similar to that, but not abstracted. It's in the name. It just has more detail, more like syntax that's not required for analysis. So if you want to do like static analysis on a syntax tree, you want to use an AST. So we have a dialect-specific concrete syntax tree. We have a way to traverse that syntax tree that's also generated by grammar. It's really nice. But then we have to hand author all of the type binding, right? So when you add a varchar and a bigint, each of these databases might treat that type coercion differently. Each of them has different functions with different function signatures, with different overloads that modify the types when they're selected and transformed at each stage. And all that stuff, unfortunately, cannot be generated or represented in a declarative language like a grammar. But the output is a logical plan and a unified one at that, so that all of the downstream analysis afterwards can be written once and repeated, no matter which dialect is resolved down to it. Cool. So just like zooming in on, I forgot this is totally our IP. No, I'm kidding, that's the open source Trino grammar. You can see from a grammar here, it's a high level syntax, right? It's relatively easy to even understand yourself. Lots of SQL keywords in here. and relatively easy to maintain, right? If I want to like tweak the keywords that are available after drop schema, I can see that if exists right there in the parentheses can be modified to include more potential SQL keywords. This is really the open source Trino grammar. It's not ours, I promise you. Cool. We even took the grammar architecture a step further, though, to enable further code reuse. By producing a G4 splitter written in Rust that would take one grammar file, we called it sdf.g4, and parse it out to generate each respective dialect-specific grammar file. That was then taken up by Antler Rust to generate a scanner, parser, and concrete syntax tree Rust module, one for each. Why was this beneficial, and what were the results? Well, we supported Snowflake, Databricks, BigQuery, Trino, and Redshift to start. We found that each dialect-specific grammar was between 1,500 and 2,000 lines of code. So it's like on the high side, it's about 10,000 lines. And the common grammar, just the SDF one, was 5,600 lines, which means our code generation resulted in an approximate 50% reduction of effort per dialect, because we were able to reuse all the rules that we wrote for other dialects, right, when they had overlap. So this kind of proves there's a very significant intersection between all of these databases, despite all their nuanced rules. There's a really good intersection, because in the end they're all SQL, right? So many of the respective keywords behave the same across them. Moving on to analyzing. We now have syntax trees being produced for each dialect. We need to bring them down to a unified logical plan. So what did we choose? We chose data fusion. It's an interesting choice. The person before me would probably also question that. But we chose data fusion. Why did we choose data fusion? Data fusion is built in Rust, first of all, easier to integrate. It leveraged a type system that we thought was going to be more of a standard, the arrow type system. And we also found it to be incredibly extensible. Many people consider data fusion to be the LLVM of databases, because it's designed to be built on top of, to build other databases on top of. And that enabled us to extend the logical plan into what we called DF++, right? So DF++ was data fusion's logical plan, but with the logical types injected in there from each respective database. So we would have Snowflake's type system embedded into the data fusion logical plan, Snowflake's functions embedded into the DF logical plan, primed for static analysis. But the structure of the logical plan maintained the same. So all the static analysis logic we wrote against the LP would maintain no matter which dialect we were processing. It was just the types and functions that were available that would differ. And this was very powerful, because we now had close to an executable plan just with a different logical type and function system for each dialect. So you can probably imagine where I'm going next, which was how do we now execute that? Well, unfortunately, introducing a logical type system that the database doesn't understand means you can't actually execute that plan, right, naturally. So we had to build custom, what we call lowering logic, right, which would lower our DF++ logical plan into a data fusion ready physical plan that it would now be able to execute. Now, full transparency, we didn't do the actual physical plan lowering. We just reproduced a DF-LP, which then data fusion took over from there and moved down to a physical plan itself during execution. But this was tricky. This was really tricky, because you had this whole logical type system which you had to map to arrow, right? We had like the geography type. That's the one example there. This is like a latitude, longitude type in Snowflake. How do you have to ask the question, how do you represent that given arrow's type system for such that the execution behaves the same? In this case, we use sort of a struct array. We also had to do the same thing with functions. We had to implement many functions in Rust that would behave the same as the way that Snowflake's functions did, or any other specific dialect. Which means we would sort of have these function signatures using the logical type system, like Snowflake's, and we would have several implementations probably to deal with all the overloads, etc., right, using arrows type schema, and then we would map that down. It's a lot of work. But the results were totally worth it, and they were super, super cool. Super fucking cool. Look at this SQL statement. Select ABC from some schema, some table. With one little YAML change, telling the system which dialect to interpret this with, you could produce entirely different results. This is a very simple example, but in the Trino case, the select ABC was considered, was projected as a selection of a column. So the results were the selection of that column. But you just change the dialect to BigQuery, and suddenly the results are now a string literal. It's a projection to a string literal of ABC. It was so cool, honestly. It was so cool to have that first moment of taking the same query and just changing a small YAML line and producing entirely different results that emulated each database. It was really, really, really fun build. Cool. So, back to DBT. We are building a new engine. And you can see the DBT branding is now on this slide. I have to remind myself that I work here sometimes. And what I like to say is that DBT solved the framework, and SDF solved the engine. So you can see this cool donut thing. Well, not really a donut, because there's a filling. A filled donut, a jelly donut. The DBT authoring layer on the outside is the same syntax that many of you probably use to author your DBT projects today. That's the semantics of models. That's the construction of DAG, refs, all that awesome stuff. And in this core in the center, we have the SDF engine, right? Which will power the deep SQL comprehension, all the rest. We call this thing Fusion, half-heartedly inspired by Data Fusion. But that's our internal code name for the engine. So Fusion, this is the new engine for DBT. Yes, we built the whole thing, again, from the ground up in Rust. On a very tight timeline. Sometimes you think that after getting acquired, it's like, oh, I'm gonna relax a bit. Quite the opposite. No relaxing. But again, the results are really cool, and the work is totally worth it, because we're seeing 30x faster parse times of DBT projects just by proxy of writing the thing in Rust. With SQL compilation at its core, that means when I do a DBT compile now, I don't just resolve Jinja. I validate the SQL that's present. I produce really fantastic metadata artifacts, like data flow understanding, column level lineage, right? We added state awareness in there for incremental recomputation and valuable sort of cache features, let's call them, and cost optimization features. Native column level lineage, obviously with a system that can now bring SQL down to a lower level. We can understand the data flow precisely. And of course, it's DBT project compatible. Very minimal changes to a DBT project. The engine just works. What's going on? I skipped a slide. Hold on. This clicker. Oh, there it is. Yeah. So what will it do for DBT users? A lot is the answer. A ton of stuff for DBT users. Maybe the core, like philosophical one I want to start with is the developer loop. So in the top right, you have the DBT developer loop today. A query is pre-processed locally. The Jinja is rendered. It's then, you can see this yellow line. It says, I don't know, is the query valid? Goes, asks the Cloud DB. The Cloud DB compiles and runs that query and returns data or an error, right? This is a long cycle. This incurs compute costs. This takes time as the developer waits for a network request, right? That loop is being put on hyperdrive by Fusion. Because the query can now be compiled and run locally, which means that the error submitted there will come back in real time, right? My SQL is validated effectively as I'm typing it. And because the system's so fast, we can do this in almost a fully interactive way, which I'll show in a little bit. But yeah, just how fast is it? It's really, really fast. I don't know why this slide started, but we're already 25 seconds into the cold parse in Python. There it goes. Yeah, restart. Come on. No, not going to restart. Anyways, the cold parse in Rust is orders of magnitude faster than a cold parse in Python. So the engine is really, really fast. And what does that power? That powers a fully interactive development experience. That means that when I'm typing the SQL here, it's so lo-fi, it crushes me. But as I'm typing the SQL, I'm getting that real-time feedback, right? So sum, this is an invalid function being used, right? I select from payments, I think, next. That's not a table, right? All of that while I'm typing. That's how fast the SQL comprehension is working in the background. That's a go to column there, right? We can take this a step further. Oh, now it's higher quality. Maybe I just have to wait a second. I'm hotspotting, by the way, because the Wi-Fi doesn't work. Good. So this is a function in IntelliSense, right? There we go. So you can see I was typing out concat. It auto-filled it for me. Here I'm typing out an alias. And you'll see the minute I save the file, it knows that there's actually an unaggregated column in an aggregation context. I need to add a group by. I need a group by payment method name. So this is the developer loop we're going for. It's so rapid, it's so fast in comparison to having to send this up to the warehouse. We can even map line spans. This one's really cool. It's just like, look at that. I'm mapping the result of the Jinja resolution in real time. So I can tweak the Jinja and I can see exactly the SQL produces. I think there's one more cool one in here. Oh yeah, preview CTE, right? So this one we interpret the SQL and then we essentially filter out everything below the CTE and show just the results of what that CTE produces, right? So all of this powered in large part by SQL understanding. And really, really fast SQL understanding. That's why that super freaking fast performance thing was so critical. Otherwise, an interactive development experience like that is not feasible. Yeah, I'm sort of curious, how many of you use VS Code today? Nice, yeah, that's good. A lot of hands, a lot of hands. That's wonderful because we are launching a VS Code extension powered by this technology. This will also be available in the dbt Cloud IDE. Really, really cool. Yeah. I love that thing. I love it. I'm very happy about it. And it is a real LSP. It's a real LSP, Language Server Protocol. How are we doing on time? Pretty good. Okay, cost avoidance is the next sort of bucket of stuff we're giving DBT users based on this technology, right? So when we have an understanding of SQL and we know about the warehouse state, we can do things like when you run a deployment to update your production state, we can know which columns have been modified since when you last made the PR. And we can only update and publish models that have been impacted by those column modifications, right? So we can get really granular and smart about incremental updates. We can adaptively orchestrate, meaning that scheduled jobs only have to run on models that depend on source data that's been updated since the last run, right? So we can combine that understanding of warehouse state with a precise understanding of the data flow to only update what's necessary. So caches, we love caches, they're great. Query optimization, so static analysis can determine when a query is written suboptimally. So I don't know if you all know this, but if you, in a filter on Snowflake, if you compare, if you cast a varchar to a date during the comparison, it prevents query pruning. Snowflake says, I actually, no, I can't filter out the partitions that I should scan because of this. I'm not totally sure why. But this is something we can catch at development time, right? Just by statically analyzing the logical plan. The logical plan tells us, oh, look at that. This person's casting a varchar to a date here, then comparing it to another date in a where filter. No go. You know, that's going to cost you a lot more money. So really powerful cost avoidance features. We've got automated data classification. This is a really, really cool one. Because we understand precisely how the data flows, more than just column level lineage, we understand the functions and transformations being applied to the columns in between each sort of model, right? We can enable the metadata to be reactive to those data flow changes, to the transformations, right? So let's say you had a metadata representing a column that was PII, right? Like an email. And you were labeling that, saying, I don't want any users in this group to be able to access that PII, right? If that PII is counted, the count function is called on that column, it's no longer PII, right? It's an aggregation. There's no way to take the information produced by that and deduce where it came from. And so we have the understanding of that transformation. We can say, okay, we'll reclassify the metadata because a count was called, you know, and we can do that at compile time. So we can produce rich metadata all at compile time that allows you to flexibly reclassify metadata as it's flowing through your warehouse. DBT just launched an MCP server. That's pretty cool. It's a really, really awesome thing. Jason Gans is in the audience. You should ask him about it. So essentially, like I mentioned earlier, AIs are bottlenecked by the same things that developers are, right? They need to validate their changes. They need to ensure that they're not selecting data they can't access. This is probably really important, right? For training models, for producing like prompts. And with that, our sort of MCP server will enable any AI to rapidly validate the SQL that it produces, right? It's a really powerful feature. So if that AI has feedback, and metadata from like an LSP that's telling it, hey, this exact line, this column is incorrect because it doesn't exist, or because you're using it in a function wrong, the AI can respond more quickly and produce better results. And the same with data classification, right? The AI can know when it can't access a column because it's classified as inaccessible to AI, So we believe that this new engine, going back to that previous point about the innovation plateau, will solve this problem and will enable dbt's framework to scale as fast as its users. I feel very confident in this. And having worked with such an amazing team in the last 4 months, I think we're going to do it. We're going to do it really well. If you want to learn more about this, you can scan this QR code and come to our launch showcase in the end of May. We're going to share all the nitty-gritty details, and you'll probably be able to install the thing yourself. Cool.